So, in continuation with our last class, I will just quickly once again tell you about the power flow diagram, and you just note that I have written actual power flow diagram, that is the exact power flow diagram. Now, when some power is inputted to the stator of a three-phase induction motor, a portion of it will be lost in the this resistance here, that is stator copper loss. Then a portion will be lost in this resistance representing the core loss, stator core loss. The remaining power as if it crosses the air gap and enters the rotor. That's why it is called air gap power. And all these powers are represented in wattage. I am thinking real powers only. So PAG is the air gap power. Now out of this PAG, a portion will be lost in the rotor resistance, and if you subtract that, you get the gross mechanical power developed by the machine, and from that, if mechanical loss is subtracted, you get the net mechanical power output. Obviously, this rotor copper loss will be simply I2, if I call this current as I2 dashed. So I2 dash squared R2 dashed into 3 times the total. This is what? This is the rotor copper loss. Total rotor copper loss, or per phase, you write per phase. Now, sometimes this equivalent circuit, that's why to represent all the losses, it is drawn like this. This is R1, this is X1. Then you have these parallel branches to take into account the core loss and magnetizing current. It will be like this. And here you have X2 dashed. And here also you can show R2 dashed. And then this resistance, which depends on slip, will become obviously 1 minus S by S into R2 dashed. Therefore, and this is your supply voltage V1. So 1-to-1 correspondence will be, this is the input power here at this point. Then stator copper loss is here, taking place here. Then core loss is taking place here, core loss will be taking place here. Then rotor copper loss will be taking place here, rotor copper loss, R2 dash, and this one is therefore the gross mechanical power, P gross mechanical, out of which a portion will be lost as mechanical power loss in the machine. Now, obviously, this we have established this important relationship that this air gap power, as you can easily see, is equal to 3 total air gap power is I2 dash squared R2 dashed by S, and P rotor copper loss will be obviously 3 I2 dash squared R2 dashed. Therefore, P gross mechanical power developed, will be the difference between these two, which becomes equal to 3, and this happens to be, as you can see, it is nothing but S times PAG. This is important, from this to this. You multiply with S, you get the rotor copper loss. And gross mechanical power will be obviously 1 minus S into PAG. So the ratio of air gap power is to rotor copper loss is to gross mechanical power is in the ratio of 1 is to S is to 1 minus S, that I did last time. Now today what I will do is this, we shall try to find out the nature of torque slip characteristics of induction motor by simplifying this equivalent circuit a bit to begin with. What we will do is this, let us draw the approximate equivalent circuit like transformer. What you do, you bring this parallel branch in front of the supply, because these are small compared to this parallel branch impedance. So this is approximate equivalent circuit will look like R1, X1, and this branch you bring it here, and here you write X2 dashed, and this resistance in the combined form I will write R2 dashed by S. This is the variable resistance. Next thing what I will do is another approximation I will do. Let us, for the first time, let us assume that R1 and X1 are negligibly small. Of course, you will not get the correct result, but negligibly small. That is the stator resistance and stator leakage reactance, let us neglect. To find out the how the basic properties of the machine can be found out if you neglect R1, X1 rather easily. That we will do first. So if you do like this, then this equivalent circuit will be very simple. This is as if all the power you give, it becomes your air gap power and goes to the rotor. That is, on the stator side, there is no loss taking place. So this will be this V1 voltage, and this is your R2 dashed by S when machine runs at a slip S. So you must understand from this to this what I have done. I have, let us assume R1 stator resistance and leakage reactance is negligibly small. Then the equivalent circuit will look like this. Whether it is possible to bring out the salient features of the induction motor so far as its operation is concerned, and that we try to do. So in this very simplified equivalent circuit of the induction motor, where only rotor parameters have been assumed to be present and stator impedance and core losses are neglected, it will be like this. Now then we can find out the expression for the torque developed by the machine. How? The torque developed by the machine is how much? We have seen last time. It is what? It is the gross mechanical power output, gross torque developed. That will be equal to your electromagnetic torque developed by the machine. So electromagnetic torque developed by the machine is P gross mechanical by what? 2 pi nr. Nr is the actual rotor speed in mechanical terms. Now this P gross mechanical is nothing but 1 minus S into P air gap power, and this I did last time. I will do quickly. This is 1 minus S into Ns I can write. Therefore the torque developed by the machine, electromagnetic torque developed by the machine, will be decided by the gross mechanical torque. That is, some portion of this torque is lost as mechanical power is a different issue so far as the machine electromagnetic torque is developed. And when these two are balanced, machine runs at constant speed. That is there. Therefore, it will be equal to P Ag air gap power by 2 pi Ns. So to calculate electromagnetic torque developed by the machine, you can calculate gross mechanical power, divide by 2 pi nr, or what you can simply do, you calculate the power here and divide by 2 pi ns, synchronous speed. Okay, either way you do, it is correct. So we will do in this way because it is simpler. So what we will do is this air gap power we will calculate in this way. Now torque, electromagnetic torque developed by the machine, by the motor, operating at a slip S, means at a given speed nr, T will be equal to P air gap by 2 pi ns. Remember, ns is the synchronous speed and constant of the machine. Now what is this P air gap power? This is nothing but 3 into resistance in that R2 dashed by, power in that resistance R2 dashed by S. That will be simply this one, 3 I2 dash square R2 dashed by S, power here in this resistance. So it is like this. This divided by 2 pi ns. This will be the speed. Now I2 dash is obviously per phase voltage is V1 divided by root over R2 dashed by S whole squared plus X2 dash squared. This is the magnitude of the current I2 dashed. So you substitute this here in this torque expression, the value of I2 dashed. Then you know the torque will depend upon what machine parameters like that. So electromagnetic torque developed by the machine will become, by putting it here, I2 dashed. So this will be 3 by 2 pi ns was there into I2 dash squared, that is V1 squared divided by R2 dashed by S whole squared plus of X2 dash squared into R2 dashed by S on the top. This is the expression. So this will be actually 3V1 square by 2 pi ns into R2 dashed by S by R2 dashed by S whole square plus X2 dash square. I mean, as it is, nothing is to be remembered, but what I am trying to tell, your torque expression is obtained in terms of machine parameters. But in a nice form, this can be expressed. That I will do now. This expression derivation is over as such. Now what you will do is this TE, this is there 2 pi ns. What you do, you multiply both numerator and denominator by a square. Some simplification you do. Then this will be, if I make any mistake, point me out. So you multiply both sides, numerator and denominator rather, by a square. So this will be what? S into R2 dashed. And in below it will be R2 dash squared plus a square X2 dash squared. It will be like this. Then what you do, so multiplying that one you get. Now 3V1 squared by 2 pi ns. You once again divide by a square. Both numerator and denominator. A square you divide. So this will be R2 dashed. Oh, this will be same. So anyway, this is okay. Now you divide by X2 dash square. Both numerator and denominator you divide by X2 dash squared. Then it will be what? S into R2 dashed by X2 dash squared in the numerator. And in the denominator it will be R2 dashed by X2 dashed whole squared plus S square. It is correct. So this will be this expression. Okay. So at this step what you do, you divide by X2 dash squared in numerator and denominator. Then your torque expression, your expression for the electromagnetic torque developed by the machine when it is operating at a slip X2 dashed S will be this one. This can be written as S into R2 dashed by X2 dashed, and another X2 dashed you write here. Just some manipulation, and below it will be a square plus R2 dashed by X2 dashed whole squared. So this will be 3V1 squared by 2 pi ns into X2 dashed. This X2 dashed comes here, and on the top you have S into R2 dashed by X2 dashed by S square plus R2 dashed by X2 dashed whole square. Now this factor, the ratio R2 dashed by X2 dashed, let is be denoted by another variable, let us call alpha. That is the ratio of the rotor resistance is to the standstill rotor leakage reactance, this ratio, and this of course will be equal to actual rotor resistance by X2, same as this one. Then your expression for the torque will be simply 3V1 square by 2 pi ns x2 dashed, and it will be s alpha by s squared plus alpha squared. Okay. Now this equation is very easy to remember. S alpha by s square plus alpha square. What is alpha? Alpha is r2 dashed by x2 dashed. Apart from that, we will see soon that alpha represents some important quantity in relation with the torque developed by the machine. So this expression is quite important. And also note that for the given machine, V1 is the rated voltage, Ns is the synchronous speed, and x2 dashed is the rotor leakage reactance per phase referred to stator. This thing is constant of the machine. If you are not changing, you will be applying rated voltage only. So this is sometimes written as some k into s alpha by s squared plus of alpha squared. So when you neglect the stator impedance of the machine, the expression for the torque is of this nature, where you should remember only this one, that alpha is r2 dashed by x2 dashed and k is 3v1 square by 2 pi ns x2 dashed. Okay. So this is the torque developed by the machine when the machine operates at any slip s. Now the next step what we will do is this: we will try to plot the value of t as a function of s for a given machine. As I told you, alpha is also constant, r2 dashed by x2 dashed. So what we will try to do, that Te versus slip, let us plot. Let us plot torque versus slip characteristics. Let us plot. Suppose on the x-axis we will plot slip. So slip we plot like this. This point is suppose s equal to 0. What is the maximum possible value of slip? 1. So suppose this point is 1, s equal to 1. And obviously you can say that if this is your slip axis, your speed is like this, speed. See, plotting torque versus slip means you are plotting also torque versus speed. But only thing, speed is changing like this. What is this speed value here? nr equal to 0, this point. And what is the speed value here? nr equal to ns. So either of this will do. And what is the expression for t? This curve we want to plot. For a given machine, if you plot, it will look, a typical curve will be like this. This axis is the torque axis. Electromagnetic torque developed by the machine will be varying like this. That is, alpha is known, k is known. You go on varying s and calculate t and plot them. It will be, a typical curve will be like this. You will find this initial portion of this curve is more or less like a straight line. And at higher values of slip, it is like rectangular hyperbola. This can easily be seen why it is so, because of the fact, see, suppose you assume S is in the lower range, that is suppose S is very low, then what will be the expression of T? Te S square you can neglect. You can neglect S square compared to alpha square if it is S is very low. Then T will become equal to, this K will be there, and a square is negligible. So some s by alpha it is coming. So it is directly proportional to slip. So that explains this straight line portion in the initial part. And suppose in the second case, if s is very close to 1, means higher compared to r2 dash by x2, then this will be t then will become very close to k into s is quite high, alpha square can be neglected. So it will be what? Alpha by s it will be. So with s it will be like this. Okay. Anyway, we will not, just to tell you this. Now the question is, in a typical induction motor, this value of slip up to which it remains more or less straight line like that, that is the slip at this point is about 10% is a typical value. That is the maximum value of the torque, as you can see, occurs in a typical induction motor at around 0.1 slip. See, this is the torque versus slip characteristics. As you can see from the curve, there will be some maximum torque the machine can develop, and that occurs at a particular value of slip. What I am trying to tell, for a typical well-designed induction motor, this value of slip here is about 10%. Typical slip is about 10% when Tmax occurs. Some figure, just not very strictly 10%, it could be 8%, 12%, like that, around 10% it will be there. Okay, this will be the torque slip characteristics of the induction motor. The second thing what I will do is this, that we shall try to find out at what value of slip this maximum torque is occurring. Okay. So that is very easy to find out. So to find out at what slip Tmax occurs. This we want. This is just a one line derivation. As you know, this is T, this is K S alpha by S squared plus alpha squared. So you just can bring this below. So this will be S by alpha plus alpha by S. So T will be maximum when this will be minimum. So d S by alpha plus alpha by S, and set it to 0, and you will obtain that S square equal to alpha square or S equal to alpha. Positive value I have to take because I know induction motor operates between 0 to 1 positive slip. So it is at this value of slip maximum torque will occur. That is here at this point. What is the value of this slip? It is alpha. In other words, the resistance in ratio, the ratio between rotor resistance and standstill leakage reactance will be of the order of 0.1. Okay, this is there. So this is the Tmax. Now the important thing what I will try to tell is the with this torque slip characteristics we can explain many things. For example, you draw a torque slip characteristics now like this. And don't correctly put the value of slip. So this is S equal to 1. This point represents the standstill condition. This is TE and this is S equal to 0. Now you just see from the very word go, that is you switched on the supply, you can now explain in a better way how machine really picks up speed. For example, if you apply full voltage to the stator winding, that is rated voltage, per phase rated voltage will be applied V1. And suppose this is the torque slip characteristics of the machine. How much is the starting torque developed? This much, is not. Now suppose the machine has to start against a load torque whose value is this much. It may be say frictional torque or whatever it is. Okay. Therefore, machine was stationary condition. You have switched on supply. At that time, S equal to 1, electromagnetic torque developed by the machine is this much. And load torque, which is to be overcome by the machine, is this much. Suppose let us assume. Then this difference of these two will accelerate the machine, which will be J d omega dt, like that. But anyway, so machine will start accelerating. So if machine starts accelerating, that is, its speed is increasing, what happens to the slip? Slip decreases, starts decreasing. Therefore, operating point will now move here. Is not? Machine speed is increasing. Slip is no longer now S equal to 1. Suppose it has become S equal to 0.9. At that time also I find electromagnetic torque developed by the machine is greater than load torque. So machine will further accelerate. So this way machine will go on accelerating. And where it will finally settle? See, all these points it is accelerating. Accelerating torque, of course, is not a fixed thing. It is changing with time. But nonetheless, it is always trying to accelerate the motor. So where it will finally settle? It will settle here. Machine operating point will move, and it is at this point you will find TE is equal to TL, and machine will operate at a constant speed. And at what speed it will run? It will run at a speed or slip that you can read from this graph and tell machine will run at this slip S1 when the load torque is TL1. Are you getting? So many things you can now explain with the help of this torque slip characteristics. So machine will be operating here. Now suppose I have increased the load torque on the shaft of the machine. It was TL1. Machine started, settled here. Now suppose I have increased load torque on the shaft of the machine. So how much is the load torque now? Suppose I have made it like this, TL2. Load torque is increased to TL2. TL2 is greater than TL1. Suppose you increase to TL2, this level. Machine was operating here. Let us explain. Machine was operating steadily at this point, running at a speed decided by this S1. Now suddenly the load torque on the shaft of the machine is increased. Speed, can it change instantaneously? No. So right at that time, that is t equal to 0 plus, when at t equal to 0 you have increased this load torque, t equal to 0 plus, how much is the electromagnetic torque developed by the machine? It is still this much. Speed has not changed. The moment you have changed load torque, rather increase the load torque from TL1 to TL2. So electromagnetic torque developed by the machine is this much. But load torque is higher than electromagnetic torque. So what will happen? Machine will decelerate. Decelerate means slip value will increase. That is operating point. Here it was. It will start moving there in the towards right. And at this point, any intermediate point, if you see, you will find TL still greater than TE developed by the machine, and machine will further decelerate. Is not? Speed will further fall. And finally, it is at this point, once again machine will find a stable operating point, because of the fact, once again the electromagnetic torque developed by the machine is equal to the load torque, and machine will run steadily here. If you further increase the load torque, finally machine will come here. So as you go on increasing the load torque on the shaft of the machine, that is, you want to draw more and more mechanical power output from the machine, speed will go on changing. In fact, it will go on reducing. But what will be the variation of the speed from this to this? About, I told you, about 10%. This value of slip, generally a typical value of slip is 0.1. So suppose if it is a four-pole machine, let us take an example. Suppose synchronous speed is 1500 RPM. That is absolute no load condition. Machine will run here. I am gradually increasing the load torque on the shaft of the machine. Then in this zone, what will be the speed at this point? That is 1 minus S into 1500 RPM. So this will be 0.9 into 1500. 1350 RPM. 1350. So variation of speed will be there, but that is not quite large. Only 1500 to 1350. This I will further explain. Okay. Now what I am trying to tell, suppose in this way I am going on increasing the torque. The point will come here, like this. In this way, suppose I come here. Load torque developed by the machine is equal to the maximum torque the induction motor can develop. At what speed machine will run? Right at this 1350 RPM. Now suppose beyond this point, I further increase the load torque. That is, I want to derive more power, mechanical power output of the motor. So I further increase. Tell me, what will be the consequence? Machine will go on decelerating because TL is always greater than electromagnetic torque. Machine will go on decelerating and finally come to S equal to 1. Are you getting? So therefore you find in a induction motor, as you go on increasing the load torque on the shaft of the machine, machine may come to a stop if the load torque demand exceeds the maximum torque the induction motor can develop. Are you getting? Therefore, induction motor will operate only in this zone. Achha, now I will ask you one question. As you can see, suppose this TL2, this one. See, machine can operate steadily when electromagnetic torque is equal to the load torque, is not? If you look at the point of intersections that your load torque makes with electromagnetic torque and where electromagnetic torque will be equal to load torque, there are actually 2 points, this one and this one, is not? So it may appear, the machine may, rather one should answer it like this: if this is the load torque, I should tell machine may operate at this slip or also at this slip. Is it not fair to tell that? Because at those 2 points, electromagnetic torque equal to load torque, and machine may continue to run steadily at that RPM. Getting? So there are two actually operating points possible, at least right now as it appears. But we will explain right now that this operating point machine cannot steadily run. It is only these operating points which this so-called state portion of the TS curve, the point of intersection of the load torque line with the state portion of the TS curve, that will give you a stable operating point. These points, it can easily be shown they are unstable. This can be easily explained. For example, you now consider this is the torque slip characteristics. Okay, machine has been started like that. This is the torque axis. and this is the slip axis, s equal to 1. This you should not make any mistake. That is often students make S1, S0. And suppose this is the load torque present on the shaft torque of the machine. And this is the electromagnetic torque developed by the machine. What I am trying to tell, the operating point could be this one as well as this one. Either of these two can claim to be the operating point. That is, it appears machine can operate at this slip or at this slip. Now, as we have seen, let us consider this point of operation. Why it is called stable operating point? Suppose the machine is operating steadily at this slip S1, developing this much torque TL. Now, as you know, to test the stability of anything, any physical system, what you have to do? You give a slight disturbance to that point and see that whether it comes back to the original steady state operating point on its own, then it is steady state, stable point. For example, a situation like this, you have a bowel and there is a ball. You give a small disturbance and leave your hand. It will oscillate and once again finally settle here. In contrast with this situation, a bowel is here where there is a ball. You give a slight disturbance, on its own it cannot come back. It will roll down to the ground. Are you getting? This is unstable. This is stable. Although it is very precariously stable at this point. This will remain stable, critically stable. But this fellow is quite stable. That is, given a slight disturbance, it will not, it will on its own come back to the origin. So, similar situation happens here. You now imagine that a disturbance has occurred on the shaft of the machine. For example, because of some reason, suppose I have slightly disturbed the operating point. Suppose speed has increased a bit. Okay, are you getting? Machine is running steadily here. Suppose by external means, say, I have tried to accelerate the machine, slightly increased this RPM. Suppose it was operating at, say, 1400 RPM. By some external means, I have made it 1410 RPM. Then what will happen? What will be the slip value? Slip will become further less. That is, here operating point will shift. The moment it shifts here, you find the electromagnetic torque developed is this much, but load torque is more. Then what will happen? Machine will try to once again decelerate and finally come here. Same thing is true if you imagine that speed is slightly reduced because of some disturbance, shaft speed slightly reduced by some amount. That is, operating point slip becomes this one, electromagnetic torque. Immediately you see it is greater than the load torque and machine will accelerate. So on its own, the machine tries to come back to the original operating point. Maybe after few oscillations because of inertia, this way, that way, but it will finally seek this point as its operating point, which is not the case for this operating point, what I am trying to tell. You imagine, let us assume for argument's sake that this at this point machine operates steadily. Machine operates steadily at this operating point. In that case, if you imagine that a disturbance is given such that the speed becomes slightly less, speed becomes slightly less. That means suppose speed becomes here. Then what do we find? Load torque is greater than electromagnetic torque. Slight shift in this operating point towards right in terms of slip axis will make what? Load torque is greater than electromagnetic torque, and then machine will further decelerate. That is, the disturbance in this direction will further pull the machine down to zero speed. That is slip 1. Similar is the case if you imagine here. This is the initial operating point. So a slight increase in speed in this direction because of some disturbance, we find electromagnetic torque becomes greater than load torque. Machine further gets accelerated and operating point goes away from it. And of course, in this way, if a disturbance come in this direction, then machine will finally come at this point and settle down. Therefore, you find that these points, although it is theoretically possible to operate the machine, but practically it serves no purpose, because a slight disturbance this way that way will either make the machine to come to a stop, or it will bring the machine to a higher speed like this. So it is for this reason this zone of the torque slip characteristics is called the stable zone of operation, stable zone. And this portion is the unstable zone. That is slip between, say, for a typical machine, if this is 0.1, you can say between slip 0 to 0.1, stable operation of induction motor takes place, and between slip 0.1 to 1, unstable operation. Of course, this 0.1 is no unique term, as I told you. It could be 12%, 13%, like that. Okay. So it is this thing one should be careful about. So the slip of the induction motor in its normal operation should be therefore varying from, say, 0 in absolute no load condition to about 10%. But as I told you that this induction motor should not be also operated very close to this point, is not, although stable this side, but it is as if approaching that what is called line of division between stable and unstable, and if it crosses this point, everything goes, means the machine comes to a stop like that. Therefore, generally the induction motor is designed in such a way that full load slip full load slip is about 5% or so. That is, SFL will be about 0.05. That is well within this limit, at the middle of this range. Generally, the full load slip is designed, so that machine will not be going to that. You can design, if you design an induction motor perhaps with a slip, say 0.09, very close to that, full load operation, a slight disturbance may bring the machine to this side and will give you wrong operation. Therefore, this point is to be understood. What I would like to tell you to keep in your mind is this: if you are asked to draw a typical torque slip characteristics of a well-designed induction motor, you should not draw it like this. This is wrong. This portion is quite steep, and in this scale 0 to 1, about 1/10 of this length will decide this one. So while sketching or telling somebody about the torque slip characteristics of the induction motor, you should draw it like this, with this one. So this is the stable unstable zone of induction motor and how it operates. Now you tell me, suppose this is the torque slip characteristics of a 3-phase induction motor. This is slip. This is Te max. So this Te max is sometimes called T pull out also, pull out torque, because machine cannot develop a torque greater than this. Machine will be unstable beyond this. So this is the starting torque. When the machine is operating under no load condition, only frictional torque present, as you can see, perhaps machine will be operating very close to synchronous speed. See, frictional torque present on the shaft of the machine will be quite low, and it will be operating very close to the synchronous speed, ns. Speed is this way. This is nr equal to 0, this is nr equal to ns. And when the machine will be operating at full load, say this one, full load torque, about 5%, this is 0.1, so this is say s equal to 0.05 or so, 4%, 5% slip. Suppose this is the full load torque. Then machine will operate at what speed? Only 1500 minus into 1 minus 0.05, that is 95% of 1500. So what I want to tell, the induction motor variation of speed from no load to full load condition is not very large. See, it was running at 1500 rpm. How much it comes? 1425 rpm. So only 75 rpm has changed in a scale of 1500 rpm. So what I want to tell, speed variation of an induction motor from no load to the full load condition is very small. That's why induction motors are sometimes called constant speed motors. Are you getting this point? The induction motors are generally called constant speed motor. Constant speed means, of course, approximately, because of this fact. The variation of speed from no load condition, no load means it will be very close to 1500 rpm. And full load, the operating slip is about 5 to 4%, so variation of speed is about 75 rpm. So the induction motor are sometimes called constant speed motors. Constant speed motors. I will now ask you one question. Suppose machine is stationary. This full load torque is present on the shaft of the machine. On the shaft of the machine, full load torque is present. Now I switch on the supply. What do you think? Machine will fail to start because load torque is greater than the electromagnetic torque during starting. Is not. Therefore, those aspects are to be seen. How to increase the starting torque of the machine, because starting torque for typical induction motor with full voltage supplied is this much only, and if it is less than the full load torque, machine will fail to start. So somehow this torque is to be increased during starting, and it should be greater than this load torque, then only machine can accelerate. Are you getting? So those aspects we will discuss. But before that, what I will just tell you, briefly start, and next time I will continue, that so far we have considered stator impedance to be neglected. We have considered so far we have considered stator impedance to be neglected. Now suppose stator impedance is also present, R1, X1, and let us neglect this no load current, that core loss component of current. Then your equivalent circuit will look like this one, X2 dashed and this R2 dashed by S. And I want to find out a more correct expression of the torque. This will be your I2 dashed. I will tell you the guidelines, you will complete it. Tell me, what is torque, electromagnetic torque, in the same line? It is air gap power by 2 pi ns. What is air gap power? Power in this resistance. So this is I2 dashed. So 3 I2 dash squared R2 dashed by S. Same thing, 2 pi ns. Only thing here, I2 dashed value will be V1 divided by the whole impedance of this one. So this will be how much? 3 V1 squared divided by R1 plus R2 dashed by S whole squared plus X1 plus X2 dashed whole squared by your 2 pi ns is here outside. So this will be I2 dash squared into R2 dashed by S. There it ends. I mean, this is the expression of the torque at any slip S. So what I will request you to find out at what slip maximum torque occurs from this expression. And next time we will discuss about that, and also we will discuss what are the effects of the variation of rotor resistance and other parameters on the torque, nature of torque slip characteristics. So next class.